All right, welcome to part 2 here on Wednesday, February the 17th. We're talking about equilibrium. So in your textbook, at the end of chapter 15, we are on page 664. Let's look at number 25. Given the value of Kp is 1.85 for this given reaction, you tell me, just in your notes right now, just tell me what would the value for this reaction be? Just go ahead and do it and see if you get an answer, an actual value. You might need a calculator. Just do A and B. We don't have to do C anymore. So on A, how is the equation in A related to the given equation? It's the reverse. So what do we do to Kp? Okay, so Kp is going to equal 1 over 1.85, right? And that equals what? 541. Okay, and then we won't worry about units. So left to right, written this way, 1.85, that means the products are going to be a little bit greater than reactants. But when you go right to left, that's going to be the opposite, the reciprocal of that, meaning that again, it's going to want to be more right to left. The SO3 is the reactant. It's going to want to be more reactant than product. So it's just, in this case, what we say, shifted to the right. And what did we do on the second, on part B? What did we do to the equation? Well, what's the difference between this equation and that equation?
It is double.
Doubled. So what do we do to Kp? Kp is going to equal 1.85 squared, which equals 3.42. All right, so just we need to understand the relationships there. Yes, sir?
Where did the numbers in A come from?
Because they tell us that Kp is 1.85 right here. So that's for this equation. So what is the value for Kp for the reverse reaction is just going to be related. It's just going to be the 1 over. Okay? So now what we want to do, well, how can we use Kc then to figure out, or how can we use concentrations to figure out what Kc is going to be, or how can we use Kc to figure out what the equilibrium concentrations are? We're going to go 2 ways, back and forth. They're going to be relatively simple problems. So, the first type of problem. Calculating Kc or Kp from concentrations or pressures. There's going to be 3 different ways they're going to give you information on this. So we'll look at all 3. The first one is calculate Kc or Kp when all equilibrium, and the key here is equilibrium, not what you start with, but what is it at equilibrium, when all equilibrium concentrations are given. Now this is the easiest of all. You probably won't see too many of these because this is just plug and chug. So when we look at problem number 31, okay? Problem 31 says methanol is produced commercially by the catalyzed reaction of carbon monoxide and hydrogen in an equilibrium mixture. Now here's the key word, an equilibrium mixture, not an initial. It doesn't say we put this in. It says an equilibrium mixture in a 2-liter vessel is found to contain this many moles of each one. Calculate Kc. All right? Well, the first thing we're going to do is write the equilibrium expression. What is Kc going to equal? Not really a rhetorical question. I was hoping for an answer.
CH3OH over CO multiplied by the concentration of H2 to the second power.
To the second power. So now all I have to do is plug in the values there. Okay? Now each one is in a 2-liter vessel, but I always just go ahead and convert it anyway. So I know the CH3OH is 0.406 moles of that. But that's got to be divided by 2 liters. Over the CO concentration is 0.17. And then the H2 concentration is 0.302. We have to raise that to the second power. Now, I think, and someone check me, I think we can just, the 2's all cancel out, that we don't really need the 2's in that. That'll work out with moles since it's all the same volume. But let's just kind of do it both ways and see. I can't ever remember on the math if that works or not. Seems like I would after all these years, but I always just put in, because it's concentration moles per liter, so we just have to put over in moles, how many liters. What does that come out to when we do all of that? Now, if they gave you grams, you have to convert to moles and then divide by liters. It's always, brackets are always concentration in terms of molarity. So sometimes they make you do extra work and calculate the molarity. What do we get? Anybody with an answer? No? Reagan's working diligently. Well, we might need to practice making sure you can put this in your calculator, right? If you use parentheses, it'll all work. If you want, you can just change it to, this is going to be 0.203 molar. This is going to be 0.865, 0.0865 molar. And this is going to equal 0.151 molar squared. If I did my math right, which I think I did. What'd you get, Lamar?
15.8.
15.8. Anybody agree with that? No? Okay. Y'all? 102?
Yeah.
All right, somebody agrees with 102? Okay, again, this is not high level here.
Yeah, it is.
0.406 divided by 2.
There's another 0 in that. The 0.4.
Now you tell me. Alright, I know, but you guys, I am old, you have to keep me square here. I mean, that's just a stupid mistake. That's just not reading carefully. Try that again. 0.0406 divided by 2 divided by parentheses 0.0865 times 0.151 squared. I get 10.3.
I think just around the decimal place where it gets lost.
Well, it would have been 103 if this was 0.4. That's where that decimal place is. So we're getting the right answer. So 10.3
Close enough.
is equal to the value of Kc. So is this going to be a product favored or a reactant favored? Product favored. Not by a lot. That's not a huge number. But there's going to be more product than there is reactant. Okay? So the easiest way to calculate Kc is you're just given everything. I mean, we're not going to do it, but if we look at number 32, okay, it says gaseous hydrogen iodide is placed in a closed container where it partially decomposes. At equilibrium, it is found. So again, they're giving you the equilibrium concentrations. Hi is this molar, H2 is that molar, I2 is this molar. You just plug it into your equilibrium expression, and you get the value of Kc. All right? Super simple. Probably not going to get one like that. Second way. Second way you're going to be given is, you're going to calculate, you're going to be given initial concentrations and one equilibrium concentration. Okay, now I was supposed to be playing Vanilla Ice, Ice Baby here, but I did because we're going to do ice tables, initial change in equilibrium. So if we look at number 35. It says a mixture of 0.1 mole of NO, 0.05 moles, and 0.1 mole of H2 is placed in a 1 liter vessel. Now it's nice when they do 1 liter because that means that the moles and the molarity are exactly the same. Okay? So I have 2 NO plus 2 H2, gas, goes to N2. We got to pay attention to states because, again, we ignore solids and liquids. 2 H2O gas. All right? So this is my equation that's given. I have initial concentrations. My initial concentration is given as 0.1 mole of NO, um, 0.05 moles of H2, and it's all in 1 liter, so the molarity, and 0.1 mole of H2O. The following equilibrium is established. At equilibrium, so how much N2 do we put in? 0. So that's what I call these are my initial concentrations. So if there's 0 of this, what's the only way this reaction can go initially? Left to right, right to left, or both ways? Left to right, right? If we don't have any of this, there's no way it can come back this way. So we know to start with it's going to go this way. But it says at equilibrium, the NO is found to be 0.062. So we have our change, and at equilibrium, the NO is 0.062. So how much reacted? What was my change between this, the initial, and the equilibrium? If it went from 0.1, and now it's 0.062, 0.038. So this is going to be minus 0.038 molar. Since it's 2 to 2, how much of this reacted? Minus 0.038. How much of this got formed? Well, 2 makes how many? So 0.038 is going to produce 0.019, right? So this is going to be plus 0.019 molar. And what's this one going to be? Plus 0.038. So at equilibrium, when I subtract this, at equilibrium, this is going to be down to 0.012. This one is going to be the 0.019. And this one is going to be 0.138. Now I have all of my equilibrium concentrations. Now I plug it into my equilibrium expression, which Kc is going to equal N2 times H2O squared over NO squared times H2 squared. Now I just plug in these values. N2, 0.019. H2O, 0.138 squared. NO, 0.062 squared. H2, 0.012 squared. Now once again, let's work on our calculator usage abilities. This one is very common, this type of problem. So this was actually part A, this is part B. Anyone have an answer?
653.7.
So 654, does somebody agree with that number, 654? Nathan says yes. Yeah, we got, y'all, hey, because everybody's struggling, those of you that are just sitting there not using your calculator, you may want to practice putting this into your calculator. It's not that's not supposed to be the hard part. Getting to this point is supposed to be the hard part.
653.7.
I trust Reagan.
I got Reagan.
You got what Reagan got?
Oh, I did get 653.
Okay, I think it's 653 point something that rounds to 4.
Yes.
654. Because really, 0.019 gives us 2 sig figs, so really it should be just 650, but we'll say 654. Did everybody follow what I did on that? You're given the initial concentrations. You're given the final equilibrium concentration of 1, then based upon the stoichiometry, the coefficients of the balanced equation, we figure out how much of each of the other one must have reacted. We know this reaction is going this way. Number 1, this is going down. If this goes down, that means some of it's reacting and forming product. For every 2 of these, 2 of those reacted. So it's going to be this much reacted, meaning the concentration went down by that much. So this concentration went down by the same amount. But we didn't start with the same amounts, so we didn't end up with the same amounts. And then this is how much got formed. 2 makes 1, so 0.038 is going to make 0.019. It's just the coefficients, the mole ratios. Okay? All right, so here's a KP problem. I don't want to do that one. Okay. Let's just look at this. Let's just talk through this one. It says a mixture of 0.2 moles of CO2, 0.1 mole of H2, and 0.16 mole of water is placed in a 2-liter vessel. The following equilibrium is established. Calculate the initial pressures. What are we going to have to do to calculate the initial pressures?
Find the total pressure and then divide each part into.
That would be a way. We'd have to find the, but how would you even find the total pressure? What are we given? We're given moles, we're given volume, we're given temperature. Ask for pressure. ME what? Ideal gas law, PV equals nRT. So you gotta do PV equals nRT 3 times. For CO2, for H2, and for H2O. You get your initial pressures. So there's an extra step. Now that's a classic AP question which would ask you to find the pressure using ideal gas law at the start, and then the next part of the question is find KP or whatever. So because the pressure of the water is given as 3.51 atmospheres, I want to calculate my pressure, which ideal gas law does in atmospheres, okay? Then I would plug that in, and I'm just going to do the exact same thing I did right here. So this problem is making you do ideal gas law. You got to know some stoichiometry, and then we have to be able to do the equilibrium part. Okay? Now, because of time factor here, we don't have time to go through and calculate the pressure each time. So, tomorrow we'll come in and we'll do some practice. Don't quit, we're not quitting yet. Okay, tomorrow we're going to come in and do some practice of these, but I want to, in the last 3 minutes, give you number 3. And then we'll just work on this tomorrow. We won't do a practice problem today, but at least you'll have the notes down. The third way to calculate Kc is you're given an initial concentration, given initial concentrations, and rather than saying how much at equilibrium, they're going to give you a percent reactive. I'm going to pass this out to you tomorrow, but just here's an AP problem from 1983. 1983.
Goodness gracious, he took so long.
That's like 30 minutes.
All right, so just real quickly, sulfuryl chloride is a highly reactive when it decomposes. That's fine. This decomposition is endothermic. A sample of 3.509 grams is placed in 1 liter, and the temperature is raised to 375. What would be the pressure? So here's a question. What would be the pressure if no dissociation had formed? This is your ideal gas law, PV equals nRT. That's how we find the initial pressure. Then it says when it comes to equilibrium, the total pressure is found to be this. Actually, shoot, I wanted to do 88. That one, this is a good problem, but that kind of shows how ideal gas law is used at the beginning. And then this is going to be a variation that we need to look at on there. But we will do all of that tomorrow when we come in. But when we look at 88, just to see, it just says is 29.2% decomposed. That's the problem we're going to look at tomorrow. And we'll go back up and do 88 just for fun. All right.